Neural networks process massive amounts of data to generate human-like text and recognize complex images, yet the internal mechanics governing these outputs remain largely hidden. When a model encounters abstract semantic concepts, like the concept of royalty, the grammatical rule of negation, or the visual texture of fur, it mathematically encodes that complete understanding across billions of mathematical weights. Research shows these concepts localize inside specific identifiable neurons. Historically, identifying which specific neuron drives a behavior within billions of parameters has been a tedious and mathematically noisy process. Without a method to map these internal semantic nodes, our most capable artificial intelligence systems function as untrustworthy black boxes. Neuro Lens is an automated framework designed to discover, label, and validate these concept-encoding neurons. The tool replaces manual guesswork with a rigorous, dual-phase computational pipeline. The first phase correlates neuron firing with targeted data probes, while the second phase proves dependency through causal ablation. Causal ablation is a technique where a specific neuron is zeroed out to measure the resulting drop in a model's performance. This framework is modality agnostic, working across text-based models like GPT-2 and vision-based models like ResNet. GPT-2 is a transformer-based model used for natural language generation, while ResNet is a convolutional neural network designed for image recognition. The system automatically detects layer types, allowing it to switch between language and image analysis without architecture-specific configuration. This automation shifts mechanistic interpretability from a theoretical exercise into a deployable engineering workflow. The pipeline begins with the Probe Builder module. This module generates balanced datasets of paired data streams, one containing a positive concept, like the word king, and one containing negative examples. The Loader module then registers activation hooks onto the hidden layers of the target model. These hooks target the multi-layer perceptron, or MLP, and feed-forward network, or FFN, layers. The MLP and FFN are sublayers responsible for processing and transforming the information passed through the model. As the data streams pass through the architecture, the hooks log the raw internal activations for every node in the targeted layers. This targeted probing establishes a behavioral baseline, providing the data necessary to isolate individual semantic neurons mathematically. Raw activation data is insufficient for identification. Every neuron is scored to filter out mathematical noise. The activation score calculates 3 metrics, beginning with the selectivity score, which ranges from -1 to +1. Selectivity is the mean activation difference between the positive and negative probe examples. The second metric is the consistency score, which ranges from 0 to 1. Consistency measures how reliably the neuron fires across all positive examples, ensuring the activation is not an anomaly. The final metric is the layer importance score. This represents the correlation between the neuron's activations and the model's final output logits. Logits are the raw numerical scores generated by the model's final layer before they are normalized into probabilities. These 3 metrics allow the concept labeler to group individual neurons into related concept families automatically. While this scoring identifies strong correlations, correlation alone does not prove that a neuron actually controls the model's behavior. A neuron firing during a test for positive sentiment might be a bystander rather than the driver of that sentiment. Neuro Lens addresses this through causal intervention via ablation. The causal ablator zeroes out a high-scoring neuron to observe the system's reaction. The tool measures the exact percentage drop in the model's overall confidence once that specific neuron is disabled. This confidence drop separates mere bystander neurons from foundational concept encoders. These intervention results are written to an ablation log, providing verifiable proof of the neuron's impact on model behavior. Causal ablation transforms interpretability into a repeatable test, locating the specific mechanics behind model cognition. Real-world validation data confirms the efficacy of this automated pipeline across different architectures. In GPT-2, the concept of royalty is physically isolated to layers 5 through 7. These neurons showed a selectivity score above 0.7 when tested against concepts like king, queen, and crown. In the ResNet vision model, the features for canine fur texture and ear shape are located in convolutional layers 4 and 5. Causal tests on GPT-2 sentiment neurons resulted in a model confidence drop exceeding 15% when the nodes were ablated. These repeatable findings demonstrate that models, whether processing text or images, encode semantic meaning through consistent mathematical structures. The final output of the pipeline is an interactive report visualizing every discovered concept family. Heat maps, Sankey diagrams, and per-neuron passport cards translate high-dimensional weights into human-readable blueprints. This level of transparency changes how we interact with neural networks, removing the need to treat them as unknowable entities. By automating probing and ablation, we can interrogate the internal logic of a model layer by layer. Neuro Lens provides a systematic method for documenting machine logic, converting opaque parameters into a verifiable schematic of model behavior.